All right. Hello, everybody. Welcome to the multi-agent reading learning reinforcement learning reading group. Today we have Lily Chu with us. Lily Chu is a PhD student at Harvard. She's developing AI techniques to address environmental planning challenges. She is focused on advancing methods in online learning and reinforcement learning for wildlife conservation through preventing wildlife poaching. Lily co-organizes the Mechanism Design for Social Good Research Initiative. Her research has been recognized with Best Paper Runner-Up at AAAI, the Informs Doing Good with Good OR Award, and a Google PhD Fellowship. Today, Lily will be talking about Minimax regret optimization. So welcome, Lily. I give it over to you.
Thanks so much, Rupali, and all the organizers and participants of the seminar. It's really fun to be joining you all, especially to have this kind of really experienced RL background in the audience. So I'd love to get into details and as Rupali mentioned, keep a discussion based throughout. So let's get started. The motivation behind my research more overall is that of environmental conservation, specifically to address the biodiversity crisis. So populations of species such as rhinos, tigers, and elephants were quite robust as recently as a century ago. But today, these numbers have declined about 96% across the board. And all of these species are now in danger of extinction in the coming decades, with over 1 million species globally in danger of extinction out of 8 million total species. So it's a huge crisis, and the UN has argued that we need to treat the biodiversity crisis as urgently as we do the climate crisis. And one of the biggest threats to biodiversity loss is that of poaching. So poachers will go through protected areas and place snares such as this to trap animals. And then to prevent poaching, we have rangers who will go on patrols throughout these protected areas to try to identify and remove as many of these snares as possible to prevent them from trapping animals. So to offer another small case study into a park, I've had that pleasure of working really closely with Shipak Wildlife Sanctuary in Cambodia, which is home to critical species such as elephants and bangtang and mudjak. And we have many years of ranger patrol data from Shipak. So this might include biodiversity signs such as elephant tracks or poaching signs such as snares or campsites. And then a principal initial level of my work was just to try to predict poaching hotspots throughout these parks. So we process these historical ranger patrol data and identify where they've spent a lot of time, where they've looked for snares, and then where they've actually found poaching activity. And we add to that any geospatial characteristics that we think might be correlated with poaching, including dynamic features from remote sensing imagery, such as precipitation and vegetation. And then we use this to generate predictive risk maps. And then after building these machine learning models, we've tried to really understand how well our algorithms are performing, not just in terms of AUC, but also on the ground. So we've instituted a series of month-long field tests in Shipak, where we had rangers patrol areas that we thought were high, medium, or low risk of poaching. And then when they shared the data back to us, we found many more snares recovered in those areas that we predicted to be high risk than medium risk of poaching, and almost none in the low risk areas, which really showed to us that we were able to effectively discriminate between relative poaching threats. And then we were when focused on high risk areas for a single month, the rangers found over 1,000 snares, which compares to a typical month where they'd find between 200 and 500 snares. So we're really excited about these results. Rupali?
Yeah, sorry, this might sound like a basic question. What are snares?
Snares are like the image that I showed early on. Yeah. It's a trap that will catch animals. So poachers will put out a snare. The animal will kind of walk through it without realizing, because it's this really small wire, and effectively go around the animal's neck or leg like a noose. And then the animal won't be able to escape until the poacher comes back. So every one snare in the park could mean the death of one wildlife.
Gotcha. Thanks.
Yes. Okay. We were really excited about the results from our field test, and we were even more excited to get this feedback from Rohit Singh, who leads the Zero Poaching Initiative at WWF, saying, I'm super excited with these results, and let's get this going on other countries too this year. So we've partnered with a conservation organization called SMART, which works on protected area management around the world to actually integrate our predictions into the SMART system so that it will become available to protected areas all around the world that are using the SMART platform. So this has kind of the deployment and development of this poaching predictive system that we call PAWS, the Protection Assistant for Wildlife Security, has been a long-running thread in my PhD research that has gone through really close collaboration with conservation organizations, and then moving all the way into deployment in partnership with protected areas worldwide. But a pervasive thread that has run across our work here is, so far we've assumed that these responses are static. So we're using a supervised learning model and assuming that there's some kind of stochastic behavior of the poachers where from month to month and year to year, their behavior is fairly static. But then we've always had this kind of underlying question of, well, poachers, if a lot of their snares are being removed in one area, they probably don't want to come back. So then they go somewhere else. And what does that behavior look like? How do poachers actually respond to our patrols? So that led us on a journey where we were taking patrol data from 2 protected areas in Uganda, Murchison Falls and Queen Elizabeth National Park, that both experience some of the highest rates of snaring in all of the African continent. And by analyzing this data, we found that if we increase the amount of patrolling measured in terms of kilometers walked in a single month, if we walked, for example, an additional kilometer, then the risk of poaching in the next time step actually went down. And additionally, we also found a displacement effect where the probability of poaching in neighboring areas actually went up a little bit. So what this is indicating to us is that the behavior of the poachers is not actually static, it's changing. So now this means that we have to do sequential decision making and kind of plan proactively, anticipating this future response. So if we want to do sequential planning in a real world setting, such as conservation, we've first kind of built this environment model and made an estimate of how the environment transitions from step to step, let's say week to week, for example. And we see that indeed there is this deterrence effect. Poachers are being deterred, they're being displaced, and the behavior is not static. However, if we want to take this environmental model that we've built and run a planning algorithm like any of our favorite reinforcement learning approaches, the challenge is that our policy might kind of be overly specific to the exact specification of our environment models and actually lead to really bad long-term results. So for example, if we wanted to estimate how strong this deterrence effect is, so if we patrol more, what is the reduction in poaching in the next month? We might get some estimate like 0.17. However, if we were to train an RL policy based on this parameter estimate, we might end up leading to a really poorly performing policy if our estimate is even a little bit off. So instead, we want to recognize that the environment model that we have, which corresponds to this really complex real-world setting, is imperfect, and that there's actually uncertainty over the estimates of all these environment parameters. So then we can be much more confident in saying, well, this we think that this parameter, this deterrence effect, is 0.17, but might be somewhere with high probability between 0.12 and 0.23. So recognizing this uncertainty and having this estimate of some interval uncertainty leads us to our the need to do robust planning to make sure that we're accounting for this interval uncertainty. So the model that we consider in this paper from UAI is that we have N targets in a protected area, and we want to learn some defender policy pi, which is telling us where rangers should go in the protected area and how much time they should spend there, how much effort they should exert in a given time step. And then we have some collection of environment parameters that we denote as this vector Z. where each element in Z corresponds with an estimate of some parameter in the MDP that describes our poaching setting. So each one of these parameters will have some interval uncertainty window that would denote by like Z underscore and Z bar. So the set of possible values of Z is our uncertainty space. And then we have a reward that we denote as R, which is a function of our policy executed in one instantiation of the environment. So each bold Z is like one selection of these ZJ values from within the interval range of each of these parameters. And then in order to train our defender policy, we want to optimize our policy with respect to a robust objective. And the objective that we consider is that of minimizing our max regret. So if we consider our reward, which is determined by our policy pi and these environment parameters v, and then compare that to the optimal policy for a given environment parameter z, which again is unknown, then we have the reward of whatever our optimal policy is, pi star. The difference between these two values, for a given z, the reward of what the optimal policy would be for z versus our reward is this measure of regret. And we want to figure out what policy pi will minimize the maximum possible value of our regret. So this is our minimax regret objective. And to give a little bit more intuition about why minimax regret, I will give an example of an experience that I had just a month ago, where my friend Ellie and I were planning on going skiing at Killington. So this was like Tuesday or something like that, and there was this forecast of a big snowstorm coming to New England that coming weekend. And there was forecast to be 8 inches of snow on Friday, which is great because we wanted to experience the snow, but that could mean that roads would be really bad. So I'll describe a reward function where we get, some unit of reward for every day that we're able to go skiing, plus some small epsilon with everything else that could comprise like the quality of our weekend, like what we're eating and like how good our dinner is and the activities that we're doing and whatnot. So Ellie calls me and she says, "Hey Lily, did you see this like forecast for this weekend? There's going to be a lot of snow. Like, what should we do about it?" And I sat there and thought about it for a little bit and said, okay, well, if it snows a lot on Friday and we aren't able to drive up, there's like not much, that we could really do because we both have to work and we can't leave until Friday evening anyways. So I'm just not going to worry about it because like the thing that is within my control, like whether or not we're going to drive up on Friday, and that's really kind of what determines my happiness, that is out of my control. Like there's not much I can do in that setting. So if we were to try to quantify that, that decision-making process, we'll consider 3 possible environment instantiations. So the uncertainty that I have here is like what the quality of the roads are like and whether we're able to actually drive up. So let's pretend that our environment parameters Z has 3 possible scenarios, A, B, and C, where A corresponds to like the roads are clear, we can drive up as soon as we want on Friday. B is like there's temporary road closures, so maybe we have to wait until Saturday. And C is that there's full road closures, we aren't able to go up at all. So then our possible reward, which is this y-axis for each of these settings, has some kind of like best policy. If we're all packed in advance and we have our like dinner planned out and we come up with all these fun activities, then we have some like optimal possible reward, this like pi star for each of these 3 scenarios. And then there's also some worst possibility, if we like are really slow to leave or if we like forget to like get gas in advance and whatnot. So then each of these is a range of like how the scope of our possible rewards under each of these 3 environment instantiations, these 3 Z values. So then the gap in our possible decisions based on things that we can control, because we can't control whether or not we end up in A, B, or C, but we can control kind of like how prepared we are and what other activities we're planning. So that gap is our decision quality gap. And let's pretend, if we like look at this more closely, that for one policy pi, like what we're going to eat for dinner and what time we're going to pack, that policy pi will yield some different level of reward in this dashed blue line for each of these 3 environment instantiations. And you'll see that the outcome of our reward is dependent on what nature gives us, what the quality of like the snowfall and the roads are for that weekend. So then the regret in each of these scenarios is the difference between our policy pi 1 versus the optimal policy. Like if we were like, super paired and like thought of all these fun activities and whatnot. And you'll see that the amount of regret that we're getting, 1.5, 0.8, and 0.05, is different in each of these 3 scenarios, A, B, and C, depending on, what nature gives us. So the setting where we kind of have like the maximum amount of regret for policy pi 1 is scenario A, in which, we didn't plan enough ahead, we're not packed in time and whatnot. But then the scenario in which we have to achieve the minimum amount of reward is actually environment C. So the maximizing the minimum reward is typically the notion of robust planning that is pretty ubiquitous in reinforcement learning. However, what we're arguing for in this paper is that we instead want to look at this notion of regret and try to minimize our maximum regret rather than maximizing our minimum reward. And the reason for that is the maximum reward criteria, which is, again, the kind of standard in adversarial RL and robust planning in RL, focus all of our effort on this worst case scenario. So it's like, if, the roads are really bad, how can we do something that's kind of like as good as possible? So maybe we buy like, tickets to a movie in Boston rather than planning on going up to Vermont. So we'd do this like worst case scenario planning. But again, the possible amount of reward that we could get, like the gap in our decision quality, is very, very small because there's very little that we can actually control in this setting. However, the argument that we're making is that we should instead focus on minimizing our maximum regret, because this is really focused on the scenarios in which our actions can make a difference, like the quality of our decisions, which is actually under our control. We want to reduce this gap as much as possible. I'll pause here to see reactions to this notion of minimax regret and the difference between minimax regret versus maximum reward.
I can understand that given an environment, you want to minimize the regret, but if the environment is not known in advance.
Yeah. Thank you, Ron. That's a great point. So the environment is not known in advance because here in this skiing example, we also don't know the environment in advance. It could be either A, B, or C. We don't know which of these it will be. So we want to find some policy that's as good as possible. And what this is suggesting us is policy pi 1 is not a very good policy because, it leads to this 1.5 like units of regret. And the equivalent in the poaching example that we're considering is instead of having A, B, or C, which are these like 3 discrete possibilities, now we're in this continuous space of what all the Z parameters could be. So somewhere between like ZJ underline and ZJ bar is, and then that for every ZJ in our environment vector, that space, that bounded space of possibilities is therefore like all the different settings under which we want to make this decision. So we don't know exactly what Z is going to be. We know kind of this closed space of values that Z could take on. So we want to minimize our maximum regret across this entire uncertainty space, which is what makes the problem hard. It is a hard problem because there's a lot of different things that Z could be. Does that help?
Yes, but why do you care specifically about the maximum possible reward?
Why don't we care?
Sorry. Like when you measure the regret, you compare with the maximum possible reward. Why do you care specifically about the maximum possible reward?
So the maximum possible reward is just what defines our notion of regret. So for each environment instantiation for Z, whether we're in scenario A, B, or C, there's some policy that would enable us to achieve the maximum possible reward for that setting. And it'd be different in every setting. So like pi star for A is different than pi star for B, is different than pi star for C. So each of these instantiations of Z gives us some optimal reward, and that upper bound will enable us to define what regret means for that scenario.
Okay, I understand.
It's just that max reward is just used to define regret. Good question. Okay. Anything else from others? Okay. So moving on, now our objective is to do robust planning subject to minimax regret. But two key challenges that make this problem really hard is that Z are continuous. So it's a very, very large strategy space. There's infinite possibilities because we have, we could have 100 different Z values, and then all of them have some interval between like 2 to 10 or 0.3 to 0.7 or something like that. So that's difficult. And then also pi is a RL policy, which is both a sequential. So we have to do some mapping of like states to actions. And it is also continuous because our actions, which is like the amount of patrol that we should do in each area, is also continuous. So this is very, very, very large, complex problem, and we want to figure out how to make it tractable. So, and then also as part of what makes this hard, pi star in this objective changes every time that we change Z. So as I mentioned before, if we're in scenario A versus scenario B versus scenario C, the optimal policy is different. So the way that we overcome this complexity is we make use of an approach called double oracle, which is proposed by McMahon, Gordon, and Blum, which treats this like minimax or maxi-min objective as a two-player zero-sum game. And then specifically PSRO applies the double oracle approach to, instead of just single shot static strategy spaces, moves it into the policy space where each sample, each like iteration of that game is actually a sequential policy. Dianbo?
I have a naive question. Why you policy pi that's not conditioned on Z?
Pi is conditioned on Z. So the the optimal pi,
the non-optimal pi, the one in the second term.
Oh, the non-optimal pi, it's like we want the non-optimal pi is something that we choose. So we're trying to find the pi that minimizes the maximum value of regret. So pi could be anything within the valid strategy space, and exactly what you're saying, we want to find the pi that is best subject to the Z that we're given.
Okay, so it's like it does not know which Z it's dealing with.
Exactly. So we want to consider pi that works best across all of these possible Z's. Yes, that's an important question. Okay, so the double oracle approach specifically will capture this minimax objective as a two-player zero-sum game where the two players in our setting is the planner that focuses on this objective of finding an optimal pi value versus a nature, which is the adversary in this zero-sum game that focuses on finding a worst-case environment instantiation Z for this problem setting. So thinking now what we want to do if we want to solve this problem is to actually instantiate oracles for the planner and for nature. So if we're able to say, okay, here's what the planner should do, and here's what the nature should do, then we can, if we can make each of those tractable, then we're able to solve for our minimax regret objective. So our planner wants to learn from sequential policy pi that minimizes regret, subject to some given value of Z. So each time the planner acts, we assume that Z is given in that iteration. And conversely, nature wants to learn some environment or optimize some environment parameter Z that will maximize regret for a given policy of pi. So the planner focuses on this min problem, nature focuses on this max problem. And then for the planner, if we were to look at this, minimizing the maximum regret for a fixed value of Z, that's very important, the fixed value of Z, then the optimal policy pi is fixed for that setting. So if we're only looking at the planner, if z is fixed, then the first term here, pi star given z, is just a constant. So then this objective is equivalent to just the standard RL objective of maximizing our reward. And then for nature, the critical challenge here is that since z is changing, this is the thing that we're controlling and optimizing over, then pi star is changing every time that we change z. So really our max z objective is a max z that maxes the pi star of this regret. So there's kind of these two maxes built in, and then pi star is this, again, difficult sequential decision-making problem. So the planner is pretty straightforward to do. We just use our favorite RL algorithm to solve for a given instantiation of z, but then our nature objective is quite hard, and that's what we want to focus on here. Rupali?
Yeah, what does max pi star even mean? How do you maximize a policy?
In the same way that we maximize the planner's policy. Like the planner's policy is to max pi, right?
That's maximizing the reward over the different pies. Oh, I see. So we're trying to maximize the regret over different optimal policies.
Exactly. Yep.
Okay.
So if we were just to look at the inside of this nature, then it'd be doing the same thing as the planner. But the challenge is because z is now also changing, every time we change z by a little bit, then the pi star also changes.
Okay.
Yeah. Okay. So again, planner's policy is pretty straightforward. Just use standard RL, maximize reward, final policy that maximizes reward. But the nature is really hard because we have this like constant shifting baseline, because whenever we change z, then the optimal policy pi star also changes. So yeah, straightforward RL objective, and then the nature's policy is really hard and requires solving our RL with every update. Rupali?
Yeah, I have another question similarly. So adding the max pi star part to this objective function, did it make things simpler? Like, did it narrow down your search space, or?
No, it doesn't change anything. We're just kind of fully specifying it a little bit more. The problem doesn't change at all. It's still the same problem that I identified earlier, which is nature wants to find a z that maximizes our regret. But maximizing regret has a subroutine that requires also maximizing pi star. So now I'm just explicitly writing that out in the equation.
I see. Okay.
Yeah. Any other questions here? Okay. So the approach that we consider that will enable reinforcement learning algorithms to optimize for this minimax regret objective, we call mirror, which is the minimax regret robust oracle, and it's an overall framework to enable minimax regret planning with reinforcement learning or general sequential decision-making policies bases. And mirror is comprised of these two oracles, the planner oracle and the nature oracle, which takes in for the planner some environment parameter and outputs a policy pi, and the nature will take in a policy pi and output transition probabilities. So if just assume for now that these two oracles are known. So we still have to go back and say how we're actually solving for the nature oracle. But for now, just assume that these are given. So then the way that the mirror framework will execute, which is again based on this double oracle approach, is we start with some random instantiation of nature's parameters. So we just pick a random z1, and then we feed that into the planner oracle, and the planner will give us a best response. So it would say, here is the policy that maximizes reward for z1. And then that gives us some value of regret, which in this case would be 0 because we found pi1 that is optimal. And then nature will best respond to pi1 and say, okay, here's a new z value that will maximize your regret for pi1. And similarly, the planner will best respond with a new pi2 that will say, okay, well now I'm going to maximize my reward to minimize regret. And then that will continue. And then each time that we add a new strategy for nature and for the planner, that grows the strategy space of each of these two players. So then we look at this small, like 2x2 strategy zero-sum game and solve for a mixed strategy Nash equilibrium. So then that will give us some distribution over Z1 and Z2 and over pi1 and pi2. So we denote the mixed strategies with this tilde, like Z tilde and pi tilde. And then that mixed strategy then becomes what the next player will want to best respond to. So now we have a mixed strategy Nash equilibrium with Z tilde and pi tilde. So then nature will then best respond to pi tilde, and then the planner will best respond to Z tilde, and so on. We keep growing this out by picking like one sample of strategy for the planner, one sample of environment parameters for nature, and then that keeps our strategy space finite for each player, and we're able to kind of iteratively go about this process until we have converged, and the change in our regret after adding a new set of strategies for each player pauses. Rupali?
Yeah, this is pretty cool. So from my understanding, the randomness is coming from generation of the Z's, right? Is like the environment is generated a little bit randomly, right? And
it's not random. It is stochastic, but it's not like Z is not a random sample. Z is a best response to the previous mixed strategy Nash equilibrium.
okay, so the Z1 has been generated randomly. Only
Yes,
Z1.
just because we have to seed our strategy space somehow.
Yeah. So then do you do like multiple iterations of this so that you cover the Z space like in a certain way, or like how do you cover, like that's what I'm thinking, because the randomness is induced okay at the first step, but what if that is taking you into like a certain trajectory, like where you're not exploring enough, and Z1 can only lead to a certain space of Z2, and Z2 can only lead to a certain space of Z3, and so on and so forth?
It's not that we're picking each like Z3 based off Z2 based off Z1. It's that we're picking Z3 based off the pi best response to Z1 and Z2. So the planner will best respond to Z1 and Z2 and say, okay, here's a completely different policy. And then Z3, we have to adapt to that new best policy. So that best response to the other agents' mixed strategy Nash equilibrium policy will force us to jump around the strategy space in like an optimal search way, rather than doing this kind of like incremental delta change.
Yeah.
So that's the beauty of the double oracle response, because we're doing we're solving for a mixed strategy Nash equilibrium at every stage, and we're having each player best respond to that optimal equilibrium strategy. Then that we are doing the most effective search throughout the strategy space.
Okay, sounds good. Thanks.
Yeah. Great questions. Anything else here? Okay, so this process of solving at each iteration for a mixed strategy Nash equilibrium, and then doing one best response, adding that to each player's strategy space, the set of Z's and the set of O pi's, enables us to like iteratively grow the strategy space until we've reached convergence and the amount of regret is not really changing. So that's the point in which we converge. And technically, the best response that going into these oracles are mixed strategies that use them with this tilde. So our mirror framework has the planner that takes in a mixed strategy best response for the environment parameters given by nature, and the outputs best response policy. And we can instantiate this planner oracle with our favorite RL algorithm that will maximize reward. So we choose to use DDPG. And then our nature oracle, as we mentioned before, has this really complex objective of finding the Z that maximizes our regret. But maximizing regret means you have to find this optimal pi star, right? So simultaneously solving for pi star in order to solve for z is hard because finding an optimal RL policy takes a little while. So if we have to do that optimal search every single time we update z a little bit, it'd be really, really challenging. So the way that we overcome this is to implement the nature oracle. So here I'm just writing out the nature oracle's objective a little bit larger, is that because the pi that we for the planner, we're using DDPG to figure out like what the best policy pi is. That is a policy gradient approach, which means that we can differentiate through our entire policy to do an incremental update each time. So what we do to implement the nature oracle is to add z's into that policy update, that gradient update that's happening every time we do one iteration of DDPG and an update of DDPG. So then our z parameters are simultaneously being updated using the same backpropagation when we're doing the policy learning for pi. I'll pause here again, just to let you digest or ask questions.
Yeah, I just wanted to make like one small point. In the interest of time, like we have about 14 minutes left, so I just wanted to let you know.
Yep, thank you. Okay. Yeah, so the beauty here is like this is a really complex objective. Like every time we change z, our pi's completely change as well. But because this objective that we have, this value of regret, is given with respect to both z's and pi's, that means we're getting a gradient estimate for z's and for pi's each time that we compute our loss function. So we can just backpropagate through the entire set of pi parameters and z parameters simultaneously. That's really like a beautiful thing about policy gradient approaches, that it enables us to do this kind of like closed loop update. So overall, our approach mirror this framework is an approach to solve our minimax regret objective by first starting with some empty strategy space sets for the planner and for nature that we denote as big pi and big z that are initially empty. So we have this like continuous strategy space, and then we just like say here are some like empty subsets of strategies from that strategy space. Then we'll randomly initiate z and then add our baseline policies, and then have this iterative process where we're doing a best response, solving for the mixed strategy Nash equilibrium, and then expanding our strategy space each time, and repeating that until we've reached some convergence and that our strategies aren't changing all that much. So then we also have theoretical results in our paper that shows that the final mixed strategy for the agent, the final policy pi that we end up with when we terminate this process, is actually a minimax regret optimal policy. So we're actually able to optimize for this minimax regret objective to some small value epsilon, because this epsilon is necessary. It's basically like a discretization error because we're in this continuous strategy space. So this theorem builds off the an extension of von Neumann's famous Minimax theorem, which was extended to continuous games with these continuous strategy spaces by Glicksberg. And then our second result is that we're able to converge to this minimax regret optimal policy for the agent in a finite number of epochs. So even though we're dealing with this continuous strategy space, we're actually able to terminate in a finite number of steps. And then as we empirically will show later on, not only is it a finite number of steps, but we can actually do quite a small number of iterations on the order of like 10 or 20 to actually get good regret minimizing objectives. Okay, so now that we've kind of like added this theoretical grounding to our mirror approach as well, we also will evaluate on experiments here using the real world data that we have from Sripak Wildlife Sanctuary for this poaching problem. So our approach mirror will denote in blue, and then we have two robust RL approaches that are using like a traditional adversarial RL notion. So the common standard in reinforcement learning at the moment is, again, maxi min reward. So that's what this middle green value will be. And then the red value is like an artificial baseline that we created that's using our notion of regret, but then with standard RL approaches. So not this iterative double oracle approach. And then we also have two baselines that are just using a fixed policy. There's no graphs yet, Lucia. I'm just describing the baselines before I put up the results. And then we have two baselines, middle and random, that are looking at either the center of the uncertainty sets for each parameter value or just a random sample from the uncertainty space. So we consider three different experimental settings where we're varying different elements of our environment setting. So different horizons, different budgets, and different numbers of targets. And then where the y-axis we have is regret. So because we're trying to minimize the maximum regret, the minimum, we want lower values on the y-axis means better performance. So our mirror approach achieves relatively low regret across all settings. And then these two adversarial RL approaches achieve much higher regret. In particular, the maximum reward setting achieves even higher regret than the artificial baseline that we created that optimized for regret. And then these kind of like static policies that don't do robust planning, but rather just pick like the center value of our uncertainty space or a random value, achieve yet higher values of regret. Okay, so this is what I have for our approach with mirror as applied to in order to enable robust planning with Minimax regret using reinforcement learning. And I have kind of a second part of this talk that will set up this problem for another real world problem setting with very different setups for how to do planning for like the nature and the planner. And that's for a maternal health setting in India. But because this y'all asked a lot of questions and there's only 8 minutes left, I'm happy to kind of end things here and we can just make a discussion from now, or I'm happy to continue on for the other and just describe this other paper. You, Polly?
Yeah, so just a simple question here. The horizon, budget, and N, are they like different environments, like different Z's or something? Like for the
They're
three different
problem. There's different problem settings. So the horizon is like what we're doing finite horizon planning for our RL agent. So it's okay if our horizon is 5 versus if we have a longer horizon of 10. Like what's the cumulative regret that we're getting across these different time horizons? Like, are we able to minimize regret with like a longer planning horizon? And we show that yes, we are. In fact, the improvement in regret actually increases with larger horizons. So, a policy that is not doing robust planning, but rather just saying, okay, like I'm just going to pick a random, value in this uncertainty space that achieves really, really high regret that kind of like increases with longer time horizons. And then the budget and N are just kind of like different MDPs for our environment.
Mm-hmm. Yeah, gotcha.
Jordy?
Just to clarify, so why is it that budget, or what is it that budget's representing? Just to understand why the results don't seem to change very much, or like why it's just doesn't seem to be relevant.
Yeah, so our budget is in the setting of how many places that we can patrol in a given time step. So if we have, let's say, 25 targets in the park, can we kind of pick one target, or can we pick 5 or 10 targets? And here, I guess the way to interpret the values of regret not changing is that if we have kind of like one place that there is like a lot of poaching, and we're able to have like the strongest effective deterrence, the other places like don't matter as much. It's hard to do that optimal planning.
Okay, thank you.
And then just so I feel like
I forget.
Yeah.
Oh, yeah, go on.
yeah, I'll just pull up this framework if that helps see people's memories too. But Ram, were you saying something? No. Okay.
Sorry, I was just saying before that if there aren't more questions, I would also love to hear about the work with maternal healthcare. But of course, like if there isn't enough time, I as well.
Okay. Yeah. Maybe I'll just if there's anything else, I'm happy to answer that. Otherwise, I'll jump forward. Okay, so I'll just briefly introduce our work on maternal healthcare. So this is in partnership with an NGO in India called Arman to help address the maternal mortality crisis. So maternal mortality is defined by the death of a mother during childbirth or 42 days after childbirth. And particularly in India, the maternal mortality crisis is extremely huge, with rates of mothers dying about 10 times higher than that of the US or Western Europe. And in fact, about double that of the UN Sustainable Development Goal target for the number of deaths per 100,000 live births. So it's a huge crisis, particularly in India. And for better or worse, many of these deaths actually are preventable if only the mothers had proper access to healthcare and information about kind of best practices. So Dr. Aparna Hegde, who is the co-founder of this NGO, Arman, argues that pregnancy is not a disease and that dying to a natural life event is not acceptable. So as a result, she started Arman, which is a nonprofit that will connect mothers with preventative health information, where mothers or pregnant women can enroll in this free program where every single week they'll receive a free phone call that has a 2-minute automated recording of, hey, here's what you should be doing for this stage of your pregnancy. But the challenge is that many mothers who are enrolled in this program will stop listening to these messages. About 30% of mothers disengage with the program. So what we want to do is maximize engagement in this preventative health program by having healthcare workers give individualized phone calls to those mothers saying, hey, it's really important. Is there anything that we can do to help? Do you need a new phone number to be connected and whatnot? And just these check-in reminders. So we treat this problem with sequential decision-making by modeling the mother's engagement as an MVP. And this approach is known as Restless, bandits. So if the mother, in each given week is listening to these phone calls, she is in an engaging state, S equals 1. And if she's not listening to these messages, she's in a non-engaging state, S 0. So we have this binary state setting. And then from week to week, she has some probability of transitioning between states 1 versus state 0. So, if she's listening 1 week, she might stop listening the next week and so on. And then the critical challenge is which mother should we call? Because if we give a call to these mothers, then the transition probability of going to the good state or staying in the good state is higher than if we didn't call. So we actually can change the transition probabilities of the MVP depending on our action. And this overall framework is known as Restless, bandits. So the challenge is that in the setting, the mother's probabilities of transitioning from state to state is, this element in an MDP, but we don't know these transition probabilities exactly. So instead, we similarly will estimate an interval for each of these transition probabilities, P, these PI and QI values. And then we want to do robust planning with respect to the uncertainty of these transition probabilities. So this paper that we have from AAAI sets up this Restless bandit problem with uncertainty in the transition probabilities as a minimax regret objective to maximize or to minimize the regret, where reward is defined as like the number of mothers that are engaging in the service calls versus not. And there's a lot of different approaches that we have to do here because the structure of this Restless bandit problem in which our actions are coupled, we have multiple MDPs, not just a single MDP. It makes the problem a lot more complex. So there's all sorts of different approaches we have to do to change the planet oracle and the nature oracle in order to make this double oracle framework possible for this setting. Yeah, so I'd be, if there's interest, I'd be happy to talk more about that like the on problem setting, the maternal health care setting, or the approach that we propose in our AAAI paper here or in different tabs. So thank you so much. I know that we're at the end of the hour, but it was really, really great to join you all, and I appreciated all the discussion throughout.
Yeah, thank you so much for coming, Lily. Yeah, I think Lucia is right. We need to have you again for the Restless Bandit ideas. And I find it really interesting that you can actually apply like similar ideas to very different like real world problems. So yeah, we would love to hear a little bit more about the maternal health problems. Yeah, if there are any like last minute questions, please go ahead. Yeah, okay, I think we're good. Well, thank you everyone for joining, and have a good weekend, everybody.
Thanks so much. Great to meet many of you. Great to see many of you again. Take care.